In the last video clip, structural engineer Angela Crowther explained how mathematics is used to survey a site prior to construction. Now she is ready to tackle the design of the building. She's going to use a process of trial and error calculation to determine an appropriate structure for the roof timbers.
So, having got our site, we can now design a school. We're going to do this by using a process of trial and error to actually size the members of the elements that go into the school, so the columns and the beams and the roof timbers, and then use this, check them against each other to go through an iterative process to design our school and come up with fixed final sizes that we need. You do this by trading off a balance between the loads that we know we're going to be putting onto the school, so they could be wind loads or snow loads or the weight of people on floors, and balance them off with the strength of the material that we have. So as you get a bigger, chunkier size element, you know that you're going to have a stronger piece of material. And that size is what we're trying to find out. So to give one example of this, if we were going to design the beams in our school, so we've got columns, and they're going to support a beam. Now this beam is going to support a section of the roof. This is the gable end. This roof is spanning here. Now, a section of that roof will go onto this beam. Other sections of the roof will go onto the other beams that we're using, but we're just going to look now at one beam which has been supported by two columns. What we need to know is how far away, how far apart we can put one column from the next. So how far this beam can span without deflecting too much or without failing. So if we draw a simplified version, we can draw our beam. We know that it's got a support point here and here, and we know that we're looking to find this distance, L. We want to find this distance between the two columns, knowing that we can safely have the beam. So what we can do is we can add a force W. This is going to be made up of the weight of a section of roof that is landing on that beam. Knowing the density of the timber and knowing the area that the timber covers that is falling onto this beam, the weight W that we're looking at working with is going to be approximately 1. Now, this becomes useful because we can take this value W and we can take this value L and we can plug it into a formula that has been tried and tested by engineers in the past to work out the amount of deflection that weight causes on a beam of that length. So how do we do this? We know that when we have a piece of material, so if you were to take a ruler, for example, and support it between 2 points, and then add a weight to it, it would deflect under that weight. So what we're going to do is we're going to work out the value of that deflection. We know that certain values of deflection are acceptable, and if they become too big, it becomes visible, which starts to scare people. They get a bad feeling when they're within that building. Or if it becomes even bigger, then it becomes more of a problem because it might crack the plaster that you've used to for the ceiling of your building. And if it was to become far too big, then it would actually, the beam itself would break. So this value of deflection is very important. Now, we know that the material we're using today is timber to design this beam. So we know from tried and tested formulae that the value of deflection is roughly the span of the beam over 200. Now, this is where the trial and error area of designing and engineering comes in. What we can do is we can say we don't know what the span L is yet, but we can try and find out. So let's say that we want to use a span of approximately 4 meters. We know that the deflection we're going to get is going to be 20 millimeters. So as long as our beam doesn't deflect more than 20 millimeters, it's okay, we're in the clear. We can use a span of 4 meters quite safely. The way we're going to do this is we're going to put it into a formula which is D deflection equals 5 WL to the 4, so that's the weight of the force coming down on your beam, the length of the beam, to the power of 4 over 384 EI. Now, E and I are constants. E is the Young's modulus of the material. I is the moment of area, depending on the section size that you're using for your beam. So we know that they're constants. 5 and 384, 5 over 384 is also a constant. So we can take all of those together and just call them K. Now, we've already worked this out, in this case using known values of E and I, to be K equals 4.38 times 10 to the minus 14. Now, plugging that in and rearranging the formula to find L, which is what we're interested in, we get L equals deflection over our constants K times by W, our weight, all to the power of 1 over 4. We know already that we've found out this value, and that has to be 20 millimetres as a maximum. We've found out K, and that is 4.38 times 10 to the minus 14. And we've found out W, that's going to be 1. Doing the maths and working back to find L, we find that L in this example can safely be up to 4.6 metres. So that means the distance between this column and this column can safely be up to 4.6 metres. Our initial trial and error calculation that we're comparing to for the initial deflection equals span over 200, we used 4 metres, 4,000 millimetres. So we know that that is less than the permissible, at which point we know that that will safely work. In our school, we have now designed that our columns can safely be 4 metres apart from each other with beams spanning between them.